This call is now being recorded.
With the new day comes new strength and new thoughts. Today is another beautiful day made for you. Begin this brand new day with new hope and determination, and you will achieve whatever success you want to achieve. Today is great, positive, and beautiful day. Good morning, everyone. This is Dainisha, Assistant Professor in the Department of Civil Engineering. Today, our Department of Civil Engineering organizing an Phase 2 AICTE sponsored 1 week short-term training program on basic of remote sensing, geographical information system, and global navigation satellite system. On this auspicious occasion, I place on record my hearty thanks to the AICTE for sponsoring this short-term training program, and also I extend my heartfelt gratitude to the management and principal for their logistic support and guidance. On behalf of Francis Xavier Engineering College, an autonomous institution sharing the knowledge around 20 years in Tirunelveli, and also on behalf of Department of Civil Engineering, I extend my heartiest welcome to each and everyone for joining Phase 2 AICTE sponsored 1 week short-term training program. Don't follow where the path may lead. Go instant where there is no path and leave a track. Now, I invite a man of distinction, Dr. V. Kannan sir, Professor and Head of the Department, to deliver the welcome address.
Thank you, Danisa ma'am. Good morning to all. Working as a professor and development of civil engineering, Francis Xavier Engineering College, Tirunelveli, Tamil Nadu. Let me also introduce my institute. Francis Xavier Engineering College is one of the oldest engineering college in Tamil Nadu state, and it is established in the year of 2000. It is accredited by NBA, and many programs are permanently affiliated to Anna University, Chennai. We are not only providing a quality education to the students, but also taking part in the national development by means of adopting hundreds of villages and providing many social activities to enlighten the poor people. On behalf of Department of Civil Engineering, it is my duty to thank our management and All India Council for Technical Education to permit us to conduct this short-term training program on remote sensing, geographical information system, and global navigation satellite system. Now it is my great pleasure to welcome our mentor and Dean for Research, Dr. N. Chandrasekhar sir, who is helping us in many ways to this STTP. And I would like to welcome today's resource person, Professor Dr. K. Kumarasamy sir, Professor, Department of Geography, Bharatidasan University, Tiruchirappalli. And I'm very much happy to welcome all the participants to this 6 days short-term training program. We are really happy to organize this Phase 2 short-term training program under the scheme of AICTE. And we hope that all the participants will be benefited and you will enhance your knowledge in this domain. Thank you.
Thank you, sir, for your gracious welcome. Every great dream begins with a dreamer. Always remember you have within you the strength, the patience, and the passion to reach for the stars to change the world. The future belongs to those who believe in the beauty of their dreams. I am profusely elated to take an opportunity to introduce and welcome the sculptor of human character and navigator of this flagship of knowledge, Professor Dr. N. Chandrasekhar sir, Dean for Research of SCAD Group of Institution. This extraordinary personality does not need an introduction at all. A noble man with idol of knowledge. He graduated from Vivo Chidambaram College, Tuticorin, and completed his post-graduation in marine geology at Cochin University, Kerala. He got PhD from Madurai Kamaraj University in 1992. His contributions to research is reflected in his consistently in the peer-reviewed journals. His ability to provide high-quality research supervision, which has been sustained over time, reflected in a number of ways. He has strong tradition of pursuing excellence of research experience in coastal geology, sedimentology, and hydrogeology. He has developed with a simple software, Beach, using Visual Basic 6.0, which can precisely calculate the beach width, slope, and sediment volume by any user-specific data. An integrated tool on web was also designed subsequently for analyzing beach morphology and wave dynamics in the year 2013. He has published more than 140 international and national research papers in reputed journals with high impact factor. He was awarded with Indo-Hungarian Educational Exchange Fellowship for the year 2011 to 2012, National Environmental Science Academy Fellowship of the year 2012, and Dr. Radhakrishnan Gold Medal Award in the field of teaching and research in the year 2014. The Lifetime Achievement Award has been bestowed to him in view of recognition of his initiatives. Considering his vast research and teaching experiences in the field of ocean sciences, Government of India and State Government of Tamil Nadu have nominated as an expert in various committees. We feel really privileged to have your supervision and backing with us all times possible. Without you, all this wouldn't have been possible. Thank you so much, sir, for your logistic support and guidance. Now, I would like to invite a noble man with the character of great heights, Professor Dr. N. Chandrasekhar, sir, Dean for Research of SCAD Group of Institution, to inaugurate the session.
So thank you, Dr. Denisha, for introducing me to the audience. Good morning to all of you. Honorable Chairman of the institution and beloved Managing Director, Engineer Arun Babu, Dr. Kannan, the head of the department, the principal of the College, Professor Velmurugan, and colleagues of the department, and the distinguished participants and resource person for this program. I have the great pleasure to inaugurate the second phase of the STTP funded by AICT. I think last phase one was conducted for a week time, introducing the concept of remote sensing, GIS and GNSS. And the second phase is to provide the kind of satellite processing and the applications. And I'm sure that remote sensing has a long way since the beginning of satellite remote sensing program in 1975. And today, Indian satellites have the capability to provide even sub-meter resolution and the temporal coverage of 15 minutes interval. So these data are being used very much for informed decision making on various applications, particularly the prospective fishing zone identification, borewell locations, identifications, forest fire detection, and disaster management, etc. So these are the various applications and the need of the remote sensing and GIS for the country's development. And the Francis Xavier Engineering College is one of the reputed engineering college in the South, and is the only college in the private sector in the South is giving focus on remote sensing and GIS, GNS, particularly in the field of research. So I am sure that the capacity that created in this institution should be, remarkably that people have been drawn attention on focusing the remote sensing and GIS to develop the capacity building in the South. So for having this background, the Francis Xavier Engineering College is trying to accomplish the vision of Dr. Vikram Sarabhai, who emphasized the use of remote sensing application for addressing the problems of common man in the country. So that is the inspiration that have been received from the Dr. Vikram Sarabhai, and we have been drawing very good support from the various R&D organizations involved in remote sensing GIS. And this is can be noted from the expert drawn from the various institutions across the country. So this shows that FXE EC, the Francis Engineering College faculty members, are all over the country. They are being closely associated for getting their mentorship, guidance, and help and assistance to develop the remote sensing and GIS program at this campus. So therefore, the mainstay of our engineering college is planning of economic and environment as well as the social program by developing the remote sensing and GIS. So I am sure the faculty members who are registered for this program and students who are registered for this program, the lectures that have been planned by the members of this institute definitely will give you a kind of the awareness and training for the student as well as the faculty members to get enhance their skill and knowledge in the field of remote sensing and GIS to apply in various aspects of engineering and technology, not only by civil engineers and other disciplines like ECE or computer science and information technology, electrical and electronics department. All that people have got an ample opportunity to utilize this remote sensing and GIS domain to develop their own basic domain to convert into a decision-making application for effective management to improve the system of administration and also to conserve the natural resource in sustainable way for the development of our country. And I am sure this a big program will give you a kind of strong fundamentals and awareness to go further in detail in making this remote sensing and GIS as career. And I'm sure that the day program of this training program will make you to enjoy by having various experts deliberations, and also you can closely interact with the resource person for having all your doubt or any support or cooperation that you require. And I am sure that Francis Engineering College will also extend fullest support who needs the knowledge on remote sensing and GIS from this platform. Once again, I congratulate the organizers for having arranged this program with the support of AICT. And also I wish that all the delegates and participants and resource person will enjoy our college campus through webinar, and also that you will get a motivation to work with us and grow with us. Thank you. Thank you. Thank you. Hello.
Thank you so much, sir, for devoting your precious time and endowing the young peoples with your words of wisdom and experience. You are an inspiration to all of us. Thank you so much, sir.
Thank you. Thank you.
To accomplish great things, we must not only act, but also dream. Not only plan, but also believe. It's a great honor for me to introduce and welcome a man of distinct vision and fountainhead of illuminating ideas, Professor Dr. K. Kumaraswamy, sir, Emeritus Professor, ICSSR Senior Fellow, Department of Geography, School of Earth Sciences, Bharatidasan University, Tiruchirappalli. He obtained his bachelor degree in geography in the year 1997 from Government Arts College, Coimbatore. MSc in Geography and PhD in Water Resources Management from University of Madras, Chennai. He was university rank holder in the graduates and postgraduate study. He was awarded UGC and CSIR fellowship for his doctoral degree and research associateship programs at University of Madras. His advanced studies were at Indian Institute of Remote Sensing, Dehradun, and at Water Resources Research Center, Budapest, Hungary. In both the programs, he was awarded distinction for his meritorious studies. He is associated with the UNESCO and German IHP-OHP programs and participated in number of activities in the Netherlands, Thailand, Sweden, Singapore, France, Germany, Sri Lanka, Canada, Indonesia, and Malaysia. He has guided 29 PhD candidates and 90 MPhil and MTech students. To his credit, he has published more than 80 research papers in national and international journals and authored 10 books in remote sensing, GIS, water resources, and environmental studies. He was awarded Professor B.M. Tirunaranan Award for his continuous research in geography by the Indian Geographical Society and UGC Indo-Hungarian Long-Term Educational Exchange Program in 2006. He is specialized in water resources management, remote sensing, and geographical information system. He was the Director of Council for College and Curriculum Development, Syndicate and Finance Committee member of Bharat Dasan University. He is the editor of the Indian Geographical Journal. He has been awarded with UGC Mid-Career Award, one-time grant, and UGC BSR Faculty Fellowship to conduct and advance research in earth sciences. Recently, he has been awarded with ICSSR Senior Fellowship to conduct research on water quality and human health in the Noel River Basin of Tamil Nadu. We are certainly grateful to him for accepting our invitation humbly and gladly to become the guest speaker for this session. We are really thankful to an idol of knowledge, Professor Dr. K. Kumaraswamy sir, for taking the time out of his busy schedule to present this session. On behalf of Department of Civil Engineering and on my own behalf, I welcome you, sir. Participants, we are looking forward on your active participation. I ensure this session will be profitable and fruitful for everyone present here. Welcome you one and all. Now, without further ado, we will turn the time to our guest speaker, the sculptor of human character, Dr. K. Kumaraswamy sir. Over to you, sir.
Thank you, madam. Respected Principal, Dr. V. Kannan, respected Dean of Research, Professor N. Chandrasekhar, the Chairman, Managing Director, and then the management of the prestigious the Technical College, Francis Xavier Engineering College, Autonomous, Civil Engineering Department of Tirunelveli. I am really happy to join with the organizers of this short-term training program funded by AICTE Phase 2 in this college. Ladies and gentlemen, I am here with you this morning to share my experience on remote sensing GNSS, GIS programs being conducted in our university for the past 30 years. Well, I am Professor Kumaraswamy. To share my experience of starting the programs in our university, way back in 1989-90, well, exactly some 30 years before, we were venturing of introducing MTech program on remote sensing. Think of 30 years before starting MTech program by an arts and science university in a village setup like Tiruchirappalli. It was 87 we started, and 88, 89 we introduced the program, and it was going on. And this lecture is on the fundamentals of remote sensing. And when we introduced the program in 89, it was called MTech program in remote sensing. After say about 10 years, it was renamed as GIS, Geographic Information System, and later, for the past 10 years, we are conducting the program in the name of geoinformatics. So Geoinformatics is the capsule program we are providing from 2010 onwards. So the thing is, let us start what is remote sensing, and then we will discuss various components of the remote sensing and so on. Maybe hundreds of definitions are there on defining remote sensing. And one of the definitions I am interested is this. So remote sensing is an integrated discipline encompassing certain branches of art, science, and technology to collect information mostly about the surface of the earth without having direct contact with the objects, using the reflected or emitted energy of EMR, applying a variety of platforms, camera systems, sensor systems, process the data using a suitable classification method to prepare meaningful thematic maps, hard or soft, interpret, do further analysis to understand and address the problems of the society, and also to support the decision makers and policy makers for evolving sustainable management strategies. As rightly pointed out by the research dean, whatever we do is not for a classroom exercise or for submitting a research project, but to give a sustainable management viable scheme that could be adopted by the decision makers and policy makers. So in that respect, it is an interesting definition. It is an integrated discipline, as you all know, that it is not only science. It is not confined to engineering or technology. And it's also a part of map making, therefore it is not just an art. It is an encompassing of various branches of art, science, and technology. The meaning of arts is that finally you prepare the maps, and that should have the aesthetic sense. Therefore, preparation needs some kind of, it should have the knowledge, perception, and then the attitude in preparing the maps. And therefore, arts comes in. Science, I mean, you need to know about the fundamentals of physics in the development of sensor or any other thing, gravity and all. You should know about the chemistry, because photosynthesis of plants or the components in rocks or mineral need the knowledge of the chemistry. And you also need the knowledge of biology, because most of the earth cover is covered by the plants, and you should know about the plants, animals, and microbes, and so on. This is the second science part, because besides these things, we should know some of science, and also the technology. It means where exactly you should keep your satellite, and what is the position of the movement, the orbit system, and whatnot. So these need the basic understanding of the technology, and therefore it encompasses the branches of arts, science, and technology. And it is mostly the collection of information. It means you have to collect the basic the knowledge of collecting information about the terrestrial objects mostly. I mean, you should collect the rocks, soil, vegetation, and whatnot, whatever that is over the surface. It also includes the ocean bodies. So you have to collect information about the surface of the earth, and you should not have direct connection with that objects. That is the base, because remote means without having direct contact. Therefore, you should not have direct contact. It should not be connected with the wire or any other object, but you have the electromagnetic radiation that is connecting, but invisibly it is connected. Then you are collecting emitted or reflected energy of the electromagnetic radiation, the EMR portion you are collecting, the reflected or emitted energy, and you are using various platforms The platforms include maybe the building top or cherry picker to drones, then aircrafts, helicopters, and satellites and whatnot. So all these platforms you are using. And you're also collecting this through the camera system, because some 30 years before, or 40, 50 years, or even the World War, we were using the aircrafts to collect the information, because these aircrafts are specially designed to take the aerial cameras and then collect information. And after this era of aircraft-based sensing system, now you have the sensor system. So you have the sensors fitted in drones to geostationary satellites. So we have the sensor system to collect information. This is the first part. So collection of data is only the first part of remote sensing. Second part of this process is the data classification. So you have to collect, you have to give ornamental things to the image data, and then you prepare the image. So it means the second part is processing. And the third part is prepare the thematic maps. So it means you make all the, say, the ornamental things and the beautification of the image data, and then you prepare the thematic maps, whether it is hard or soft, whatever it may be. And that is not the end. The preparation of map is not the end, but it is only the beginning. So it means based on that, you have to interpret and do further analysis. So ground truth data collection, and then various classification methods and so on. So all these things require the analytical part, and that is interpretation is basic thing. So you use the elements of interpretation, and then get the basic map. That is first part. Second part is go further analysis using classification methodology, and then also adapt the models, and finally you prepare the maps or a model or whatever it may be. And whatever we do is not for, as I said earlier, classroom purpose or for submission of a project report, but to understand the problem and address the problem. So understand first, and then you apply your knowledge, perception, and all these things, and then give a report to the decision makers. Say, for example, if it is given to a district collector, then the district collector in turn will implement it immediately, or he will send it to the policy makers, maybe the government, state or center or whatever it may be, and they will evolve the management strategies. So it means finally it should be useful to the society for evolving certain sustainable management strategies. Therefore, remote sensing constitutes a number of integrated elements, starting from discipline to management strategies. And if you think all these things in mind, then your eye, the brain, the human element is the best way of comparing the remote sensing system. Let us see how. And why do we need remote sensing? What is the purpose of applying your remote sensing? It's a scientific data collection, because science needs verification and then testing. Therefore, this scientific data collection means in situ survey. So wherever in those areas which you cannot enter into, that is remote or inaccessible areas, and also if you do not have the way to reach the place, then you can make use of this one. And frequently take the data. Frequent survey is possible, because once it's 20 days or maybe you get it. And then low cost, because initial cost will be higher, but later you will get the benefit of the low cost in long run. And accuracy is very, very high. because if X surveys a place, then the result will be different, and then Y surveys it will be different, and so on, because all these things can be overcome by using remote sensing. So another thing is unbiased, because we have the prejudice in collection of data, processing, and then all these things. And this remote sensing does not have the bias, and therefore now it is legally accepted. Even the courts accept the remote sensing data for judgment purpose. And the applications are unlimited, because you cannot count. If you look at the journals of remote sensing, GIS, and all remote sensing journals, you can look at several heterogeneous applications of remote sensing. However, we have limitations. It is not the answer to all our day-to-day problems, because whenever we go for lecturing, the students used to ask whether that will solve this problem, that problem, and so on. But it is not the end, because it gives certain guidelines for addressing the problem. And we have the limitations at the air, atmosphere, limitations on surface, and limitations with respect to water also. So there are several limitations. And minute things cannot be measured, because if you look at your eye, then probably you can detect several minute things, but these minute things cannot be detected through the remote sensing. We have limitations in terms of sensors. And the information within the pixel is very much generalized. Say, for example, if the pixel size is 80 meter, 10 meter, 1 meter, or 50 centimeter, whatever it may be, but within this, that 1 square meter area, all the objects within that is generalized, and a number is given, digital number is given. So based on that, you can find out which is dominating, and then you make the classification that is different. However, finally, we used to say that, however, it provides useful and scientific information for studying various environmental parameters, because for providing or collecting information for a large area, you need to collect various parameters, and this is the only handy information system. And we know very well that geoinformatics includes all the 3 components. And the 3 components include, one is remote sensing, and the second is GNSS, Global Navigation Satellite System, and the third one is GIS, Geographical Information System. And today we are going to talk only about the one component of this geoinformatics, that is remote sensing. Even with that, we are going to talk only about satellite remote sensing. If you use aerial camera or aerial system, aerial platforms, and then interpret that, then that becomes aerial remote sensing. Generally, this is the general definition. And if you use satellites, whether it is a geospatial, or whether it is geostationary or sensing from the satellites, then that part is called satellite remote sensing. And if you use the thermal part of thermal region of EMR, then thermal remote sensing. And then if you use microwave, say for example radar, then that part is called microwave remote sensing or radar remote sensing. And finally, we are also using ground penetrating radar as a component to a remote sensing element. And all these things are the components of remote sensing. Say, for example, when we introduced MTech program way back in 1989-90, we had aerial remote sensing for a couple of papers. Say, for example, aerial remote sensing, then photogrammetry, 1 or 2 practicals. Then satellite remote sensing, image processing, satellite remote sensing, basics, and then 1 or 2 practicals, then thermal, micro, and even GIS and so on. So we introduced, and that was remote sensing at that time. Then comes GIS. So when we introduce GIS, you have so many other components and also include remote sensing and GNSS. If an MTech program is provided in GNSS, it means you have to introduce these 2 components, then only you go in depth about GNSS. So it means these 3 cannot be separated with the computer basics. Let us move into the remote sensing in detail. So remote sensing, if you consider remote sensing as a unit, then that should be considered as a system, because system means you need an integrated elements that are functioning to achieve certain purpose. Say, for example, if you have the human body as a system, then you have various components, various limbs, and then say nerve system, bone system, blood system, and so on. So all these systems, if it functions well, then you call this as a proper system. Likewise, if you have so many integrated elements in this system, then you call this as a remote sensing system. The first and foremost thing is the energy source. This is the sun is the source of energy. Number two is the B is interaction of the EMR with the atmospheric elements. Second part. The third part is after crossing these atmospheric elements, then it reaches the Earth surface and interacts with the Earth surface future. And the next part is you have the platforms, you have aircraft or helicopter or satellite, whatever it may be. You have a platform, and there you have fitted with a camera or a sensor system and collect the information. And if it is an aircraft, then directly it will come to the laboratory, and then you can process the data and then make the photograph. That is different. But if it is a satellite, then you collect the data and then send the signals to the ground station. So for example, in India, you have a ground station at Sadnagar, Hyderabad. So there we are collecting the information, and then again you have to process the information. So E is transmission, F is processing. So in National Remote Sensing Agency, NRSA, now NRSC, National Remote Sensing Center, they process the data, and then you prepare the maps. So G is interpretation and then analysis part. Either you purchase the data and then process, or they themselves process the data. And finally, you prepare the thematic maps to address the problems and also to support the decision makers. So this is the entire system in the remote sensing system. Let us start with the electromagnetic spectrum. The spectrum consists of frequencies of electromagnetic radiation. So this electromagnetic spectrum consists of electric waves and then the magnetic waves. So low frequency and then high frequency. This electromagnetic spectrum consists, it ranges from, say, radio waves on the extreme side and gamma ray to the shortest wavelength with the high frequency. And say, for example, here is the gamma rays. Say one is gamma ray, and then you have the X-rays, ultraviolet rays, then visible spectrum, infrared region, then the radio waves, microwave radio waves, and so on. So normally we use about 400 to 700 nanometer for our visible spectrum. Normally that is the visible spectrum of our human eye. And let us look at each spectrum one by one, and then we will go for other applications. Say ultraviolet region is the spectrum with the lowest or shortest wavelength. The rocks and minerals illuminate more of ultraviolet radiation, and also it has the power to penetrate certain extent in the water bodies. So when the Landsat was launched, initially it was called the ERTS, Earth Resources Technology Satellite by America, USA. They started the band with 4, 5, 6, and 7. So they thought that ultraviolet could be used maybe later, and therefore they left bands 1, 2, 3 and started with band 4, 5, 6, and 7. So after a couple of years, they realized that the UV could not be used for remote sensing activity. And Landsat 2 onwards, they started with band 1, 2, 3, 4. So if you look at the literatures of 1970 to 73, 74, then all literature would say or will illustrate bands 4, 5, 6, and 7. Then the visible spectrum. The visible spectrum is the very small portion which starts with 0.4 to 0.7, precisely 380 to 700 nanometer. This is the color the human eye could detect. So for example, the violet color 0.4 to 0.45, then say this is micrometer, and 0.45 to 5 is blue region, violet and blue. Then comes green, 0.5 to 0.6. Then 6 to 7 is yellow, the orange and red. Normally we call this as a red. So these are the three major regions the human eye could detect. Then comes infrared region. The infrared region starts with 0.7 to 100 micrometer. This is 100 times more than the visible spectrum that is a human eye could detect. Then this infrared region could be classified or divided into three groups. One is near infrared, we call NIR, 0.7 to 1.3 micrometers. Mid IR, MIR, that is 1.3 to 3 micrometers, and emitted or thermal IR, 3 to 14 micrometers. And the thermal IR is the radiation that is emitted from the Earth's surface, that is in the form of heat. The microwave region starts from 1 millimeter to 1 meter, and it is a longer wavelength. It is useful for transmitting the information from one place to other because it has the penetrating power. It can penetrate haze, light, rain, shadow, the snow, clouds, and smoke. So it means it has the penetration power and it is being used widely. Because of this region, the microwave region is dealt as the micro remote sensing, especially the radar, radio detection and ranging. And the first part is over. So the energy, so the sun's energy is the prime source, and it is emitting from the sun, and it is coming to the Earth's surface. And before reaching the Earth's surface, the radiation has to pass through a certain distance in the atmospheric, Earth's atmosphere. So there you have the particles of gases, and you have the atmospheric, say the dust particles and so on. So if you have the particle size in different sizes, then you have the scattering. So you have the Rayleigh scattering, Mie scattering, non-selective scattering, and so on. So probably you might have studied earlier. And a part of the EMR is scattered, and another part is being absorbed. So through the ozone, carbon dioxide, and water vapor, they absorb a portion of the EMR, and the remaining portion reaches the Earth surface. Say, for example, sun's energy is coming, and then it is interacting, it is being scattered, it's being absorbed, and remaining portion comes and interacts with the Earth surface feature. Then the area EMR, the remaining portion of EMR that reaches the Earth's surface is called the atmospheric window. So if you have a window, then whatever the energy that is blocked by the, say, the rods or wood or whatever it may be that is fitted in the atmospheric, in the window, the remaining portion enters into the room, and therefore this window concept applies to room also. So this visible portion of the spectrum that our eye could detect is more sensitive and corresponds to atmospheric windows. Say, for example, these gaps are the portions that are observed or emitted by the atmosphere, and all these colors are the atmospheric windows. So only these portions are used for remote sensing activity. Then, after reaching the Earth's surface, it interacts with the Earth's surface features. So there are three forms of interaction. One is absorption, second is transmission, and the third part is reflection. Say, for example, based on the physicochemical and biological composition of various elements on the Earth's surface, they absorb. So some portions are being absorbed, some portions are transmitted to the nearby area. They are being stored or whatever it may be. And some portions are reflected. So it means they absorb certain portion and emit during night time or even daytime. and some are transmitted to the other bodies, and some portions are reflected, because now we are using only the reflected energy. Now you have the reflected energy, and let us look at, we have various platforms to collect the reflected or emitted energy. So the platform is one that is mounted above the surface of the earth to collect the reflected or emitted energy. It could be ground based, or it could be air based, or it could be space based. So it means there are three major possibilities. Besides that, you can have so many other classifications. One is a ground based. Within a few tens of meters, if you collect the information, then they are called ground based or ground bound. They include some kind of top building. If you climb on the top, and then if you view an area, and then if you take information, then that is also a ground-based information. Then if you climb on the ladder, like or cherry picker or crane or whatever it may be, you should be away from the ground and then use a camera system or a sensor system and then collect the information. That is a ground-based data collection. Air-based means you can use the aircraft or helicopter or drone to collect the information. Then they are called air-based or aircraft-based or drone-based information. You can use
Hello.
a system or
Excuse me, sir. Your PPT is not at all visible.
really.
PPT is not at all visible for the audience.
Oh, really? I'm sorry. I'm sorry.
Yeah, please enlarge it. Okay.
Yeah.
Thank you, sir.
Ma'am,
No, it is visible.
ma'am, please pin it.
No.
Ma'am,
You
please pin Kumarasamy sir, so that it can visible the PPT.
Oh. Oh. Is it visible?
Yes, sir. It is visible?
Okay. Is it okay?
PPT is not visible, sir.
Not visible, sir.
Sir.
Oh.
So earlier it was
It is
visible.
not visible, sir.
Oh.
Earlier it was visible.
Okay. Probably if you have any defect in audio or video, kindly contact me. Okay.
Oh, so it was visible. Now it's not visible.
I see. Only now it is not visible. Okay.
Yes, earlier it was, sir.
Okay. I'm coming.
It was visible, but we are not able to read any of the contents.
Oh, really?
That was the problem.
We were able to read.
Oh, from the beginning or only now?
No, from the beginning itself, we were
From
not
beginning,
able
sir.
to read the contents. Only PPT is visible, but
Right.
it is not readable.
No.
I had to
Yeah,
put in the
please.
chat also.
Yeah, please pin to sir. Like you need to pin on sir's icon so that you can read it.
Oh.
Okay, thank you.
Okay, well.
Is it okay now? Hello?
Sir?
Okay, sir. Okay.
Is it okay? Okay. Is it okay?
Sir, please
Hello?
share your screen.
Is it okay or? Hello?
Sir, please share your screen.
Yeah. Screen sharing. Screen sharing.
Yes, sir, it is visible now, sir. Thank you.
Thank you, sir.
Oh. Okay.
Okay, sir.
Yes, sir. Yes, okay, sir.
Sir.
So we are talking about the atmospheric window. So it means whatever portions that are observed by the atmospheric elements, and the remaining portion that reaches the surface of the earth is called atmospheric window. How energy is interacting with the earth surface features, and you have three possibilities. One is absorption, transmission, and then the reflectance. And you have various platforms to collect the reflected or emitted energy, and they could be ground based or air based or space based. And we have also talked about various ground based data collection platforms, and we have also the air based data collection, including the aircrafts and helicopters and drones. Now let us look at the space-borne platforms. They are the satellites. Mostly these satellites are placed at a certain distance, say for example 400 to 36,000 kilometers away from the Earth's surface. And you have the satellites, and these paths of the satellites are called orbits. And orbit selection is based on the altitude, the orientation, and the rotation of the Earth's surface. And they are continuously rotating around the Earth, and therefore they are maintaining their paths. As on date, we have more than 1900 satellites in orbit. And these satellites include the polar orbiting satellites and the geostationary satellites. And let's look at the polar orbiting satellites. Why do we call polar orbiting? The name itself says that it moves over the pole, and therefore it is called the polar orbiting satellite. Normally, the satellites are placed at say 400 to 1100, 1200 kilometers from the Earth's surface and move over the pole. Say, for example, if the satellite is over the North Pole, and it takes about 100 minutes to reach South Pole, and in another 50 minutes it will reach North Pole. So normally, one rotation or the orbit takes about 100 minutes. It roughly varies, maybe 98 minutes or 1 or 2 minutes and so on. So it flies over the pole, and therefore it is called a polar orbiting satellite. And it is related to the sun's position, the azimuth, and therefore it is related to sun synchronous, because when it crosses a particular point on the Earth's surface, the time is fixed. Say, for example, if it moves at 9:50 in the morning, then it will be there. It will be continuously at 9:50 over this orbit till it reaches the South Pole. It means because the Earth is rotating from west to east, and the satellite is moving to from north to south, it is related to the sun's position. And the third is it is called the resource satellite. Why? Because it is very, very precise, because these satellites are low altitude satellites and flying at say 400 to 1200 kilometers, and they collect very precisely the information. And for that reason, it is called the resource satellite. And examples are Landsat, the American Landsat, the French SPOT, Indian IRS, and so many hundreds of satellites. And the second group of satellites is called the geostationary satellites, and these satellites are mostly used for weather observation, telecommunication purpose, and also some classified reconnaissance surveys. Earth is rotating from west to east, and these satellites are mostly placed over the equator, and the purpose of the satellite is to view a certain portion of the Earth's surface. Say, for example, this particular satellite is assigned to view maybe the Arabian Sea. So this satellite is placed at 35,800 kilometers precisely. Sometimes we call 36,000 kilometers. So these satellites are placed at say 36,000 kilometer view to view a particular portion of the Earth's surface, and the movement is from west to east. It means the satellite's movement is synchronized with the speed of the Earth. So all the 24 hours, the satellite will be viewing only that portion of the Earth's surface. So it means 24 into 7, the satellite can be viewed from this portion of the Earth's surface. And interesting part of our satellite remote sensing or even aerial remote sensing is a sensor. A sensor is an electronic device that measures a portion of the or minute portion of the Earth's surface. And it is also called as a charge coupled device. There are two types of sensors. One is a passive sensor. If a sensor collects the naturally emitted, naturally available energy, then it is called a passive sensor. And if it collects artificial sensor, if you eliminate and then if you collect back that energy like this, then that is called an active sensor. Now, there are two concepts which are very, very interesting to us in remote sensing is the field of view and then the instantaneous field of view. If you have a sensor fitted in the satellite and then if it collects the information for a smallest elemental area, small portion of the Earth's surface by an individual sensor, then that is called the IFOV, instantaneous field of view, for that particular sensor. You have thousands of sensors fitted in the satellite, and at that time, the sensors in the satellite, say the collection of sensor or sensor system collect that information about the Earth's surface, and the entire area viewed by the collection of sensors is called the FOV. So FOV stands for the entire sensor system, and IFOV stands for individual sensor. And there are two elements in scanning methodology. So scanning is the collection of information by the individual satellites. And there are two ways. One is cross-track scanning, that is a disc broom type. And the second is a long-track scanning, that is a push broom type. These are the two methods. The cross-track scanning means it is collected by a set of, say, the sensors, because earlier the sensor development was very crucial, and therefore only few selected sensors are being used in the satellite, say for example Landsat. So they used only this kind of sensing system, that is cross-track scanning. So when the satellite is moving in a particular direction, then the mirrors, they move left and right and then collect the information. So this is the cross-track scanning. Track is there and this information is collected across it. Then this is called the disc broom. The collection is perpendicular to the direction of the movement of the platform or the satellite. Then after a couple of years, they developed another methodology like a spot. They use the along track scanning. So it means when the satellite is moving in this direction, you have several thousand detectors and simultaneously they collect all the information required for the entire area, say for example 20 kilometer or 30 kilometer or 60 kilometer. And they collect the entire area simultaneously, and that FOV is the field of view, and they collect, and then that system is called broom or long track scanning or push broom type scanning. A very interesting part of remote sensing is the resolution. The resolution is the ability of the sensor to collect the information in 4 ways. One is spatial, spectral, radiometric, and temporal. So if you have an individual sensor in the satellite, they are assigned to collect information about the smallest elemental area through IFOV. So IFOV is a circle, and within that you make a big square, then that is a pixel or the spatial resolution area. So the minimum elemental area the sensor detects is the spatial resolution. And in how many spectral bands the satellite is assigned is the spectral resolution. Radiometric is how this is the EMR you desire to collect is split into various radius and quantity is the radiometric resolution, and then how frequently the satellite comes and collects information is the temporal resolution. Let us look at the spatial resolution. It refers to the minimum elemental area the satellite sensor could detect, as we have given. It is a IFOV, instantaneous field of view. The area on the ground is called the pixel. That determines the spatial resolution of the satellite. So for example, here is the pixel size. Say for example, it could be in Landsat 1, 2, 3, 4 and so on. It was 80 meter by 80 meter. The pixel size of Landsat was like that. And now it has refined to say 30 meter, 10 meter, 5 meter, 2 meter, 1 meter, and even 0.5 meter. So now we have landed up with 0.5, half a meter or 40 centimeter. That is the finest resolution. So some other assignments, if you have only one resolution of this size, it gives only this color. Some shade you will be getting. If you have 2 into 2, you will get somewhere you have higher density, lower density, and so on. So if you have 5 by 5, you could identify some objects at the center. If it is 10 by 10, then say for example, if it is 100 meter by 100 meter, imagine like that. If it is 10 meter by 10 meter, you could identify very big, okay, some letter is there. And still half a meter, then 10 centimeter, 20 centimeter, and 10 centimeter, it means if it comes, then you can identify the object very precisely. And spectral resolution is the ability of the sensor to collect a specific wavelength interval of EMR. So how you are defining the sensor to collect, whether you have 4 spectral bands or only 1 spectral band or hundreds of spectral bands like hyperspectral. So how many spectral bands your satellite has determines the power of the satellite sensor to cover. So normally you have multispectral sensor in 4 bands. Say for example, blue, green, red, and infrared region. And nowadays you have hyperspectral with more than 100 spectral bands viewing the same area and collecting the information in various very precise spectral regions. Then the third component in resolution is the radiometric resolution. It is the ability to discriminate even the slightest difference in data collection or energy collection. So it means it is based on the bits and binary formats. Each bit is an exponent of power 2. Say for example, if you have only 1, 2 to the power 1, it means only black or white. If it has more than that, 2 to the power 2, 3, 4, 5, and so on, if you have, normally nowadays we use 2 to the power 8, it means 256 grayscales ranging from 0 to 255, because 0 does not emit or reflect any energy, and 255 is the maximum energy reflected. So in that way, 0 to 255 is the 8-bit data. Now we call 8-bit data or 9-bit data. So this is 8-bit data, 256 grayscales, and this is 6-bit data, 64. It does not give enormous value of information, but this gives. Likewise, if it is a 4-bit data, that is 0 to 15, only 16 levels are there, and precision will be less. Likewise, if it is 3-bit data, only 8, 0 to 7, it means very coarse resolution is there, and so on. So 2-bit is black or white. So this is the one. So likewise, you have so many bits of data collection. And finally, coming to the temporal resolution refers to the time interval between repeated coverage of the same area. How frequently the same satellite or the prototype satellite comes and collect the data, that determines the temporal resolution. Say, for example, if the satellite comes today over Tirunelveli, when it will come again, whether it comes after 18 days, 16 days, or 22 days, or 28 days, how frequently. This is enhanced if we have two satellites, the prototype satellites, say for example IRS 1A, 1B. So it means if we have the prototype, all specifications are the same. If we have two satellites of the same similar type, then the temporal resolution is divided into two. So it means if it comes to 22 days, if we have two prototype satellites, then once in 11 days you will get the data. And if we have the tilting possibility of the satellite, say for example, if we have the tilting possibility of the satellite to move left or right, say for example, if we have, if the satellite moves over Tirunelveli, and then if you want to cover area of Tuticorin, then you tilt the satellite to the east and then collect the information from Tuticorin. Or if you have some other information, if you want to collect from, say, Trivandrum, then you can tilt on the other side and then collect the information. If you have the tilting possibility, then the temporal resolution is reduced. Likewise, you can proceed. Then these are the two time data, one on the top and the bottoms are two temporal data sets. You can find out the differences. Then finally, you have the key. We know very well that all objects on the Earth's surface reflect and emit it uniquely. So it means the physical, chemical, and biological characteristics of individual objects on the Earth's surface has unique character of behaving with respect to reflectance or emittance. So you have the sensors fitted in the satellite or a drone or aircraft, and they collect the information about an object. Say, for example, if you have a meadow, then the energy from the sun is reflected over the meadow, and you have a sensor, and then you are collecting the information. So the reflectance is based on the physical, chemical, and biological characteristics. So these determine the reflectance nature, whether the meadow reflects more of blue, green, red, or infrared region. And you need to collect information about the meadow, and then the data collected from the satellite could be processed. So for processing the satellite data, you need the ground data. So you have to go with the spectroradiometer, use the same sensor used in the same satellite, and you collect in the 4 bands or any number of bands. Say, for example, if your satellite has 4 spectral bands, and the same sensors are used in the spectroradiometer to collect the information that is a meadow, and collect the information on blue, green, red, and infrared, and you can plot it as a graph. Say, for example, you have collected for the meadow, say, for example, 0.4, then 0.4 you are collecting. Say the percentage of reflectance is plotted here. So 30% is 0.4. Then at 0.6 or 7, then you have the peak. Then again you have the depression and so on. So plot all these things and then make a graph. Likewise, you can make the graphs for hundreds of objects and use this graph as a ground data, and then you use this for classification methods, classification methodology. You have class supervised, unsupervised, whatever it may be. Then find out how many acres or how much of area is covered by meadow. Likewise, you can collect a number of coconut trees. You collect the data for coconut tree and then make the classification and find out how much of area is under coconut tree. or groundnut crop or paddy or whatever it may be. So all these things are possible because of this key, because this is the most interesting topic in remote sensing. Then let us look at the Earth surface, Earth observation satellites one by one, and then go for applications. Say, for example, Landsat was launched in 1972, and it was functioning at till 1978, and so on. So these are all the satellite series. And Landsat 8 is in process, and they are aiming for Landsat 9. So they are using the OLI, that is the Operational Land Imager. One is in use, and they are going to develop it as 2, and then TARS, Thermal Infrared Sensor, TARS-2. It is going to be launched in mid of 2021. And these are all the Landsat series. Initially, they had earlier, I was talking about 4 bands, and it was developed as a TM spectral bands with the 7 band, and the 6th band was thermal band, 10 to 12, 10.4 to 12.5 micrometer. It is used to the heat stress measurement possibilities are there. Otherwise, these are all normal bands. Followed by that was the French spot. French spot and our Indian remote sensing satellite were almost of the same size, same period. 1986, 87 onwards they started, and then it started working in 86. Then ICROS data, that is the latest one, 1 meter resolution. You can identify even the minor features on the Earth surface. Most precisely, you can map it. And we have finer satellites, even for very finer satellites are there, including the GeoEye, WorldView, QuickBird, then the SATIUM data, Astra data, Reset, SAR, then Hyperion, then LDCM, and so on. So all these give in various spatial resolution, spectral resolution, radiometric resolution, and then the temporal resolution. That resolution determines the capability to interpret and analysis. Then let us look at the Department of Space. That is, the Department of Space comes under direct supervision of the Prime Minister. The Prime Minister of India looks after Department of Space. Under Department of Space, you have the ISRO, and its centers are functioning. And ISRO headquarters is at Bangalore, and the satellites are fabricated at Bangalore. The launchers are fabricated at Thiruvananthapuram, Tumba, and they are being launched at Sriharikota. Then the data reception center is at Sadnagar, Hyderabad, and they collect the data. And data verification is at Ahmedabad, where they develop the sensor. And again, if they give green signal, then the data is disseminated through the NRC, National Remote Sensing Center, to the users. And if you want to get training, then you have to go to Dehradun for higher trainings. And if you want to get higher studies, then again you have to come to Thiruvananthapuram. IIST, Indian Institute of Space Science and Technology is there, and then you can conduct higher studies. Besides that, there are hundreds of centers which are supporting the activities of ISRO, and you have more number of NNRMS, RRSSs, then other EduSat programs, and other supporting centers. Then these are all the evolution of our Indian satellite system, starting from IRS, starting from Bhaskara, then you have IRS system and all these things. Then you have excellent Cartosat and then resource satellites. So Cartosat and resource satellites are giving enormous potential for mapping of the resources of India. And then comes important missions of ISRO include all these satellites, as I mentioned earlier. Then your NAVIC satellite, that is what is the navigation satellite, the constellation is there. Now we have to replace our GPS system, that is a global positioning system, to NAVIC, and probably in a couple of years, we will be all accustomed with using the NAVIC system. Then, as I said earlier, you have NNRMS, then you have the EduSat programs. Then you have the Bhuvan geoportal is there. Then whatever data you want to download or you want to see the developments, you can go to the Bhuvan and then find out the recent developments. Then let us look at in a few minutes various remote sensing applications. Say, for example, this is South India. This is a typical false color composite. We are using mostly the false color composite for our remote sensing activities, mostly because plants reflect more of infrared than green, and therefore we are normally give red color for plants or photosynthesis activity. So Kerala has more vegetation, and Tamil Nadu does not have, but Sri Lanka has in between. So it means if you look at Congo upland covering parts of Salem to Pollachi, this area, it is almost a dry region. It is almost comparable to South Tamil Nadu. This condition, it is under cloud, otherwise it will be the same of Coimbatore, because all these areas are dry. Here is a metro dam. And the white patches are the clouds. And it is mostly used in geology and minerals for rock type identification, because based on the reflectance characteristics, we can find out various rock types. And it's also used for classifying the minerals. Then find out lineaments, where you have the fractures of more than half a kilometer that could be detected. Then wherever you have the oil-rich areas, wherever you have the domal structures, there you have the possibility of the oil and natural gas zones. And if using the thermal data, you can also identify the volcanism. If the temperature is increasing slowly, it means that there is an increasing possibility of volcanic activity in that region. Then it is also used in town planning, because there are hundreds of applications. I am giving only a few. And in town planning, you can also use the images for mapping various landforms or land uses. This gray areas are the built-up areas. Say, for example, this is Madras city or Chennai, and this is Triplicane area. And Triplicane area has very, very limited vegetation, and it is given gray shade, so gray tone. And this gray, and if you look at Marina Beach, here also you can see the gray color, gray. And this is a dry sand, and if it is admixed with water along the coast, then it appears as if it is a building. Then you have to use various spectral bands to classify and then find out this sand, and this is a building. So that kind of classification, so you need several spectral bands to classify them. Because otherwise, if you look at the naked eye, probably you may confuse that there are buildings all along the sea. The second most important is the oceanographic studies. You can identify various ocean currents. Then plankton identification to identify the fish pools. Then coral reef analysis, sediment movement, as Professor Chandrasar is known for this kind of works. And also the oil spill analysis, where you have oil spill. If you have a collision of two oil tankers in the midst of a sea, then you cannot do the analysis. You cannot do the process or what is that oil spill detection or investigation at the sea. Rather, you can apply a model and then find out where exactly the oil will be coming and then being deposited. You apply a model and then find out. Likewise, atmospheric weather forecasting. If you have a cyclone, then find out based on the cloud movement. Then ocean current movement also you can identify that based on the temperature you can find out in which direction it's moving and so on. So all these things are coming under weather forecasting. Now it is called weather nowcasting because simultaneously you can find out whether the cyclone is moving in this direction and this direction and so on. So that is possible because you can use the windy what is it software, and then you can find out the track of the cyclone. Then another interesting part of our discussion is the ground penetrating radar, because ground penetrating radar is a supporting mechanism in remote sensing, and this is a pyramid, and this is a ground penetrating radar. And only thing is it is costly because it ranges from say 50 lakhs to 1 crore and above. We use the same kind of ground penetrating radar in Keeladi investigation, that archaeological survey investigation, and also used in Srirangam to find out the hidden temples beneath the Srirangam island. And this is a pyramidal thing. And then if you want to identify the paths in the inside this pyramidal structure, you can use the ground penetrating radar with the different antennas, and you can find out. And the second part on the right down is the tunnel. When you are constructing a tunnel, then you can use the ground penetrating radar to find out the strength of the walls. And it will give where you have the low structures, and then you apply some material, and then you can construct the tunnel safely. The bottom left is nothing but an urban center where you have the platforms, and over the platform we walk, and beneath that is the say the cables, electric cables and telecom cables, and you have the sewerage system pipelines, and then drinking water pipelines, and all these things are there. And if you have some defect in any one of these systems, then you can make use of this instrument, that ground penetrating radar, to find out, and then take only 2-3 slabs and then repair, and you can just cover it within a few hours. You can do this repairing work. Otherwise, you have to dig for kilometers or hundreds of meters and then do the service. The bottom right is this ground penetrating radar is an integral part in defense system. Nowadays, all these military operations are being done where you have snow cover. So in the snow cover area, if you have some missiles or if you have some dead bodies beneath the snow cover area, then you can use this ground penetrating radar to find out if you have some unusual things. Here, for example, here, say for example, this is a snow cover, this is a line. And if you have unusual thing here, say for example, your dead body is here, then if you find out that this is a dead body, then apply the same concept here, here, and so on. So you will not dig all these places. So dig only this portion and then other portions and so on. So this is very, very useful in our defense. So almost all high altitude, say the military operations are supported by the ground penetrating radar. And probably this is the end of my lecture. So remote sensing, as we know, we have started with as an integrated discipline. And then various, say the electromagnetic regions, then data collection, then data processing, and various applications we have seen. And I have given only a bit of information about the remote sensing because it is a very big program, because we used to conduct this for 2 years, and sometimes the certificate course is given for 1 year, and giving it in 1 hour or 1.5 hours means only very, very precise and only the important concepts I have learned. Thank you very much for listening. Thank you, madam. Hello.
Participants, if you have any queries, you may raise now.
Yeah.
Participants, if you have any queries, you may raise now.
Maybe sleeping.
If you have any queries, you may raise now.
Sir, I have one question.
Yes.
In your Lancet series,
Yeah.
you mentioned one point that is geocoded. Can you please elaborate the concept of geocoded? It's not clear to me. That's why I'm asking for you to please elaborate the concept of geocoded to me.
Now, probably that is in the image processing. The first part of image processing is that where the raw data is collected by the sensor system, and that is being processed in the laboratory. You have to register using the projection method. The different projection methods are applicable to various countries depending upon their location, whether they are in the North Pole, South Pole, 60 degrees, 70 degrees, 80 degrees north, or at the equator and so on. So all these things are determined by the projection methodology you are using. So over the projection, you place your digital data and stretch it to your convenience, and then make them to read or to make layers which could be suitable for your machine. So it means your machine should be able to recognize your digital data, which is projected over a particular projection. So depending upon the projection, the raw data is stretched or compressed and being studied. Okay, so it's in image processing, you'll be reading this in the first part. Second part is classification, first part is this.
Okay, sir. Thank you, sir.
Any other queries?
No doubt means two possibilities. Only is they might have understood it completely or bounced back.
Any other queries? Okay, sir.
Okay.
Shall we wind up the session?
Okay, thank you. If you have nothing to discuss, then probably yes.
Participants, any other queries?
Probably those who are going for Board of Studies, I request them, because it is an additional information. We have been teaching remote sensing for the past 30 years. That is next to Institute of Remote Sensing at Anna University, Chennai. We were doing this program. We were conducting the program from 1980, 30 years. Initially, it was remote sensing. So if you look at the history of remote sensing, in the Indian Institute of Remote Sensing, it was only Indian Photo Interpretation Institute. That is an offshoot of ITC Netherlands. And initially, they were doing only the photo interpretation. In the photo interpretation, the second phase was photogrammetry, mathematical measurements. And when satellite remote sensing was introduced in 1972, then 1/3 of the program was covered by satellite remote sensing, And after a couple of years, image processing was also introduced. So 25% photo interpretation, 25% photogrammetry, 25% satellite remote sensing, visible interpretation, and another 25% of image processing. This was a system of courses being taught at IIRS or even ITC, Netherlands. Then came your GIS, GNSS system, and all these things, and your learning program software and all. So all these things are added slowly. And now, encompassing all these courses, you have a name called geoinformatics. So better you use the word geoinformatics rather than calling separately remote sensing, GNSS or GIS. So the thing is, for the past 10 years, we are running only the geoinformatics. Rather, if it is an engineering field, we call geomatics. However, you use the word geoinformatics because nowadays all the advertisements for employment are given as geoinformatics rather than geomatics or geospatial technology or whatever it may be. Whenever you go for curriculum design, you use preferably geoinformatics. And within that, you have the aerial remote sensing or satellite remote sensing or GNSS of GPS or any other system or GIS. So better to use the word geoinformatics rather than separate identities like remote sensing, GNSS and GIS. That's my request, because most of you are teachers, and then you may be going to various universities and deemed institutions, and keep it in mind these words, because even geomatics was used a couple of years before, and geospatial technology is there, but the program or course should have geoinformatics flavor. Thank you.
Thank you, sir.
Yes.
Be thankful for what you have. You will end up having more. I would like to take this opportunity to express my sincere gratitude to our guest speaker, Professor Dr. K. Kumaraswamy sir, for sparing his valuable time for making this session a very meaningful one. Thank you so much, sir, for your devoting precious time and endowing the young peoples with your words of wisdom and experience.
Welcome, madam. Welcome. Thank you. Thank you.
Thank you. Thank you so much, sir.
Yeah.
Finally, I extend my heartfelt gratitude to all the participants for your active participation. Thank you one and all for your cordial cooperation. Let's break for a lunch and assemble back sharp by 2 p.m. Participants, the feedback link is posted in the chat box. Please submit your feedback. Thank you. Thank you one and all.